Swayam Prabha. Digital India. Educated India.
Welcome to this lecture number 3, which is in which I am going to continue from where I stopped in the previous lecture, that is on groundwater level fluctuations and environmental influence. And here we know that it should be our endeavor to maintain the groundwater level, which may be water table in case of an unconfined aquifer, or it is known as the piezometric surface in case of a confined aquifer. So, this groundwater level should be maintained at the optimum range. It should not be, it should neither be too shallow nor should it be too deep, and to maintain this optimum level of groundwater during all the times. So, we need to study the reasons for reasons based on which the groundwater level fluctuates. So, some of the reasons are listed here. The first one is the stream flow variations, followed by meteorological and tidal phenomena, and urbanization is also one of the parameters which influences the groundwater level fluctuation. Followed by earthquakes, external loads, and so here land subsidence. So, here let me also write land subsidence, etc. So, these are some of the reasons or causes for the groundwater level fluctuation. And let me also continue. So, in the previous class we were discussing about the secular as well as seasonal variations. While the secular variations represent the variation in the groundwater level over a period of more than a year, seasonal variations, they represent the variation in the groundwater level within 1 year over different seasons. And there is also third type of variation, which can list it as the short term variation. So, in this case, so it is basically daily or diurnal variations, which is very commonly observed in municipal water supply wells. So, essentially here you can say this short term variation is a daily, represents the daily or diurnal variation. Seasonal variation represents the average annual variation, average variation within an year, and secular variation represents the variation in the groundwater level over a period more than a year. So, we need to consider all the three, and during all the periods, right from period ranging from less than a day to a period which is say around a year to a period which is greater than that, maybe a number of years, could be 5 or 8 or 10. Okay, so, all these things we need to consider. Now, let us consider firstly the stream flow and its impact on the groundwater levels. So, let us consider in this figure a stream with bed shown along the sloping bed shown here, and then there is an impermeable strata. Let this impermeable strata consist of a hump as shown here in the middle, and because of this hump in the impermeable strata, So, the water streamlines, the groundwater streamlines will show an upward trend, and especially in the hump. So, where the height of the impermeable strata is at its highest. So, the some of the groundwater streamlines, they will be above the ground. So, they become surface water streamlines, and so in this portion, so that is say from here to here. So, this water table will be above the ground level, whereas to the left of this the water table is below the ground, as well as to the right of this section the water table is below the ground level, or in this case it is a stream bed level. So, here what happens is, so this portion, that means from the hump to the portion where the groundwater streamlines have transformed themselves into surface water streamlines. So, it will be acting like a effluent stream or a gaining stream. So, because here what happens is, so the all the groundwater will contribute as effluent, or as will contribute to the stream flow. Similarly, the downstream of the hump, so what happens is, because it is the downstream part of the hump. So, here what happens is, the surface streamlines which were appearing here, they again develop a downward orientation, and then they get transformed into groundwater streamlines. So, therefore, from this point onwards downstream, the water table is again below the ground level, and this portion between the hump and the location where the surface streamlines again get converted into groundwater streamlines. So, that will behave like a losing stream or an influent stream. So, in this case what happens is, because of the water table higher than the water table in the adjacent one, so the stream will lose. So, through infiltration, as well as through infiltration occurring at the bed as well as the banks. So, therefore, it will be acting like a losing stream or an influent stream. And in the middle portion, so it is the rising water in a stream channel from the emerging groundwater flow. So, this is how the stream flow will affect the groundwater level. So, many times this stream flow, the effect of the stream flow on the groundwater level is also visible, especially in case of floods, the flood wave. Let us consider in this case a flood stage hydrograph, which represents the variation of stage, which is essentially the water level in the stream at a particular location with respect to a standardized datum such as the mean sea level, and its variation with time. And in this case, the time values are represented in terms of flood periods. So, flood period is the period, basically it starts from the duration, from the time instant when the stream flow or the discharge goes on increasing abruptly above the base flow, which is basically the groundwater contribution, and then again after reaching the peak flood, during which time there will be peak stage. So, this is the peak stage here. Again it starts, the flood wave starts receding. So, the flood level as well as the flood discharge gets reducing, and finally it reaches the normal level. So, this period from the increase, from the time instant when the flood wave started increasing to the time instant when the flood wave started decreasing. So, this is known as a flood period. So, here it is indicated as the time instant between 0 and 1. So, here this is the flood stage hydrograph, and the difference between the initial water level, which is the here in Indian terminology it is known as the no flood level or the danger level, and also the highest flood level, that is the final water level, that is the water level during the flood peak. And this initial stage of flood is also the final stage, because after the flood wave recedes it again goes back to this one, and here this is the ground surface which is slightly above the flood flood peak stage. And in this case, now let us consider how the bank storage volume as well as the recharge and discharge vary in case of a flooding stream. And so now let us consider the bank storage. So essentially this bank storage volume is the volume of flood water which gets stored in the banks, of course which includes beds also. And here what happens is, so this as the flood stage goes on increasing from the initial level to the flood peak stage, so the bank storage volume also goes on increasing, and when the flood stage is at its peak, the bank storage volume is also at its peak, and as the floods stage goes on decreasing, the bank storage also goes on decreasing, but more gradually, not as abruptly as the flood wave. So here in this case, if the time for the receding flood stage hydrograph is maybe of the order of say 40 to 50% of the flood period, whereas in this case the time for the reduction in the bank storage volume, it may be almost say at least 2.5 times the flood period. So it is more gradual here. And now let us consider the recharge and discharge volumes, so which occur due to the water entering the bank storage and the water leaving the bank storage. So here initially when the flood wave starts and the flood stage goes on increasing from the initial level to the flood peak stage, so the recharge goes on increasing and it reaches the maximum, and again so this recharge, then the recharge goes on decreasing, and at this time instant when the flood stage is at its peak and the bank storage volume is also at its peak, so here so the recharge volume, which essentially is represented by the volume bound by this curve, so this recharge volume is also the maximum. So here this is the peak recharge intensity, and this recharge intensity goes on decreasing, and then the recharge volume, so this is the area here, so that is maximum. And once the recharge is maximum, then what happens is the water starts leaving the bank storage, and so that will appear as a discharge. So this discharge, which starts from the time instant of the flood peak stage, it starts increasing initially, reaches a peak somewhere between the flood peak stage and the first flood time period. So somewhere in between, so this the discharge volume is the discharge intensity is maximum, and then so like the bank storage volume, so then onwards the water leaving the bank storage will also be gradual. So essentially this area which goes on increasing represents that is the water leaving the bank storage, and again so in about 2.5 to 3 times this one, so it shows the it again comes back to its original value. So this is the impact of stream flow. So previously, in the previous case we discussed about the the groundwater level in case of a river which is having an impermeable bed with a central raised portion or a hump, and in this case number 2 we studied the variation of the flood volume, especially the bank storage volume, as well as the water entering the bank storage during the recharge process and water leaving the bank storage during the discharge process. So, these are some of the cases of stream flow influencing the groundwater level. Now, let us come to what is known as the base flow, and this base flow, as the name itself says, so it is the flow which is existing in a stream due to an extended contribution of groundwater. So, obviously the stream flow, it originates from the groundwater flow. So, this base flow is a stream flow portion which originates from the groundwater flow. Now, let us consider a flood hydrograph. As I was mentioning here, so this is the total hydrograph, which we can also call it a flood hydrograph. Say somewhere here, this during this period there is a precipitation or rainfall, and then because of that, so there is a surface runoff increase, and then it starts the flood hydrograph and it reaches the peak. So, this is the peak discharge or the peak flood discharge, and after that it goes on decreasing, and again it will reach the total discharge will be equal to the base flow, wherein entirely it is the base flow which contributes to the total flow from this time and beyond. So, now here let us study the variation of the base flow. As we discussed in the previous case, so because during this period recharge is taking place, the groundwater recharge is taking place, and unless the groundwater gets saturated, so there cannot be any discharge. So, therefore, this essentially the dotted line from here to here, this represents the recharge phase, and then there is no this one, and if we from this point onwards the discharge starts. So, this discharge, it goes on increasing, reaches a peak, and then it starts decreasing, and so finally it starts gradually decreasing, and it reaches from this point onwards. It is only the base flow which is contributing to the stream flow. There is no other contribution to the stream flow beyond this point. But if we consider if we neglect the bank storage, then what happens is, so the base flow hydrograph, which is essentially the plot of the base flow with time, it shows less fluctuation. So, so here what happens is, so this base flow hydrograph, in this we are neglecting the bank storage, and because of this one, so it is showing the minimum base flow does not reach 0, because there will be always some one, but this is not the actual case. So, this is just the base flow hydrograph when we neglect the bank storage. So, here the minimum base flow is also less, is slightly more than the 0, which is the actual minimum base flow, and the maximum base flow is slightly less than the actual maximum base flow, which occurs somewhere here. So, like this, so it is the base flow which essentially is the one which provides the this one, that is which provides the extended groundwater distribution over space and time, and it is essentially this base flow in hydrology. It is represented by the various infiltration indices like the phi index, the W index, so which represent essentially the infiltration part, and then so especially this W index, the initial abstractions are also shown. So essentially, so the base flow represents the minimum total flow which exists during the period wherein there is no flooding. Now, so this represents the base flow variation during a flood hydrograph, the actual variation shown by the dotted line, and the base flow hydrograph neglecting the bank storage shown by this line, which shows a higher minimum and a lower maximum. Now, let us consider the other factors, such as the impact of evapotranspiration on the groundwater fluctuation. So, in the previous class we mentioned that even though groundwater, it is below the ground, so always there is some small portion of groundwater which is closer to the surface, which is very close to the surface level, and it is affected, it is subjected to evaporation. And so therefore what happens is, so because of this small, that is the portion of this ground flow which is directly subject to evaporation near the surface, so there in the surface, near the surface, so the evaporation expressed as a percentage of pan evaporation is very high, as you can see here. So this is some in the range between say the surface and say 0.5 meters, or say maybe 1.45 meter, which is 1.5 feet. So around this range, in this top layer, so the groundwater evaporation, which will be almost 25 to it is more than 25%, and even it reaches as high as say 50% of the pan evaporation rate there. But as we go deeper and deeper, so this the evaporation effect, it will be less and less visible on the groundwater fluctuation, because so what happens is, so this is the groundwater is at a depth below this 0.5 or say 0.45 meters, and therefore what happens is the groundwater evaporation of groundwater expressed as a percentage of pan evaporation, it goes on decreasing, and even it may be so at deeper depths it may be practically negligible, it may be of the order of say 5% or even less than that. So this is how the groundwater fluctuates due to the effect of evaporation. So the effect is significant in the groundwater layer which is at the top, that means from the surface to say 0.45 to 0.5 meter below the ground, and below that the fluctuation that of groundwater level due to evaporation, so that will be significantly less. Now let us also consider the effect of transpiration, because as you know, evapotranspiration consists of evaporation which is occurring at the open surface, or the open water bodies, or the bare soil. The soil moisture gets evaporated there, and the transpiration is basically the water which transforms into the vapor form due to the metabolic activity of the plants. So the plants, they during the process of metabolism, so through this stomata openings, so they give out water in the form of water vapor, which is known as transpiration. And here say let us consider a day in a few days in summer and the depth of water table, and as you can see here, so this day 1 represents a 24-hour period, similarly day 2, day 3, day 4, all of them represent 24-hour period. And as we all know, so the temperature is maximum sometime immediately after the midday. So therefore, during that period the transpiration rate will also be maximum. So therefore, the depth of water table will be the highest, that means the water table will be the deepest at that. And again, as the evening approaches and then as the at the midnight and then so beyond that, so what happens is, so due to the reduction in the transpiration activity, so the depth of water table, it shows a slight increase. So this may be of the order say a few centimeters, maybe something like less than, definitely less than 10 centimeters, generally of the order of say around 5 centimeters. Then again the next day it happens the same thing. What happens is, so here somewhere immediately after the midday, okay, the transpiration is the maximum, the rate of transpiration is the maximum, so the water table depth is minimum. So this kind of daily variation of the water table depth due to transpiration, it follows a you can say this is a sinusoidal wave. Now let us consider the effect of the vegetation, evapotranspiration, essentially because it is extremely difficult to measure evaporation or transpiration separately, because when plants grow on the ground, so there are some areas where there are plants which are planted artificially, or plants which grow out naturally, whereas in the neighboring areas, so there may not be any plants. So essentially, so in such case, so there will be loss of water from evaporation in the bare soil or the soil or the area where water is the plants are watered by say flooding and other similar processes. So here what happens is, so therefore it is a well known practice to express this total loss due to evaporation and transpiration together as evapotranspiration. So here, see, in case of a bare soil, so the evapotranspiration is the depth to water table, the plot of say depth to water table versus evapotranspiration, it follows this curve. So therefore, so at this one, so at this depth, so there is 0 evapotranspiration. So this could be say a few meters, maybe 2 or 2 to 5 meters or so, depending upon the type of soil and the presence of the impervious strata below. And on the other hand, say wherever there is a shallow rooted vegetation, so these consist of plants whose roots, they do not spread say more than say 1 meter from the ground surface. So in such case what happens is, so at the ground surface the evapotranspiration is the maximum, and then as we go deeper, and obviously this depth, the depth wherein the evapotranspiration will be practically 0. So this depth will be higher than the depth due to the depth observed in case of a bare soil. So here, so the variation of evapotranspiration and the depth to water table in areas having shallow rooted plants or crops or vegetation, it follows this one. Obviously here this here as you can say, this is a bare soil, so this evapotranspiration is entirely due to evaporation, whereas in this case, so if you can say this is due to evaporation and this is due to transpiration. So and at this depth, which may be say something like say 1 to 2 meters. So, here so the at this depth and beyond, so the evapotranspiration becomes practically 0. And now let us consider deep rooted vegetation, like such as the large trees. So, for example, I can give this banyan tree. So, this banyan tree, it is one of the one wherein the roots, so they also grow and they also reach the ground, then they grow bigger and bigger, and thereby giving additional stability to the banyan tree. And in this case, the roots may go even few meters deep also, maybe sometimes even maybe tens of meters deep, rarely. So, here what happens is this the plot of evapotranspiration and the depth to the water table. So, it will follow a curve which is even, which is having a at the ground level, the evapotranspiration is even more, because it is a deep rooted vegetation, and when it is deep rooted vegetation, it also has a large number of leaves as well as stem through which this transpiration takes place. So, therefore, the evapotranspiration at the ground level is larger, and also, so up to this this is basically it represents the root zone depth, which may be of the order of say few meters, say 5 to 10 meters. So, only beyond that the evapotranspiration becomes 0. So, therefore, so this is this diagram shows the variation of evapotranspiration with the depth to ground with the depth to water table for bare soil, shallow rooted vegetation. So, wherein we can say the vegetation is the root zone depth is say less than 1 meter or so, less than 1 meter, whereas deep rooted vegetation wherein the root zone depth is even up to say 8 to 10 meters or so. So, in this case, so this is the variation. So, now let us come to the variation or the fluctuations in the groundwater table due to other meteorological phenomena such as the atmospheric pressure. And we know that, so it is the atmospheric pressure which is the prerequisite for a low atmospheric pressure is a prerequisite for precipitation. When wherever there is a low pressure formation, so there what happens is the water, the atmospheric moisture, which is as well as the moisture which is in the clouds, it has a tendency to precipitate, and this precipitated the clouds with water, atmospheric moisture condensed in them becomes heavy, and then there the precipitation starts in various forms of precipitation. So, here what happens is, so as the atmospheric pressure decreases, so here, so these peaks, because the atmospheric pressure, it is shown to be in the graduation, it is the higher atmospheric pressure is shown in the downward direction. So, therefore, this as the atmospheric pressure increases, so there is no possibility of precipitation. So, therefore, the groundwater, the well water level, which essentially represents the groundwater in an unconfined aquifer, it will be at its lowest level. And as the atmospheric pressure decreases, so it represents these points. So, here, so there is a possibility of precipitation, and then due to precipitation, the well water level, which also represents the groundwater level in an unconfined aquifer, increases. So, like that, so this is the effect of atmospheric pressure on the groundwater fluctuation. In this case, we have considered only the unconfined aquifer. Now, let us come to the effect of precipitation in general and say rainfall in particular on the groundwater level fluctuation. So, here let us consider the weekly hydrograph, which represents the amount of precipitation which has taken place during that particular week. So, in this case, this rectangle represents the precipitation depth in the week number 1. Similarly, this represents the precipitation depth in week number 2. So, like that. So, this is basically a stacked bar graph with the width of each of the stacked bars equal to the duration of 1 week. And in this case, now in red color, the average water table elevation in the wells, which represents the groundwater level in an unconfined aquifer, okay, is represented. In this case, as you can see here, so this is basically here we can say this is we can consider this to be the monsoon season in a region, say in India, where the monsoon is significant, and this one. So, here what happens is, as long as there is some amount of average weekly precipitation, so this results, and the average weekly evapotranspiration is somewhat less than this. So, this the groundwater, the average water table elevation will go on increasing, and there are some places where the average water table elevation is almost stagnant. So, those represent the weeks wherein the total weekly precipitation as well as the total weekly evapotranspiration is more or less same or slightly less. In that case, it also shows slight decreasing trend. And in this case, so here say this during week number 17 and 18, there is absolutely no precipitation. So, in this case, the precipitation amount, the weekly precipitation amount is 0, whereas the weekly evapotranspiration amount is significant. So, therefore, it shows the water table shows a lowering trend. So, that is shown by this, and then again on the 19th week. So, there is some precipitation, and because of that the water table again, and as long as this the depth of precipitation is slightly more than the average weekly evapotranspiration. So, this water table goes on shows a slight increase. So, like this the various meteorological phenomena, okay, will impact the groundwater level fluctuation. Now, let us consider the tidal range, the effect of tides on the groundwater level. In this case, we know that, so then in English there is say that time and tide wait for none. So, these tides essentially are daily tides which occur with a time period of say 12 hours, I am sorry 24 hours and 50 minutes. There are also the spring tides, and so in a duration of say 24 hour 50 minutes, so a point on earth will be closest to another similar point on moon. So, essentially these tides occur due to the attraction between the earth sun attraction, earth sun, earth moon, as well as sun and moon. So, this obviously of course sun and moon, it will not have any effect on the earth, but at least the attraction between earth and sun as well as attraction between earth and moon, earth and moon. So, this attraction results in the daily tides. So, which will so in a period of say 24 hour 50 minutes, there will be 2 spring tides, there will be 2 high tides, and there will be 2 low tides. And then similarly during summer, and then during winter, spring as well as autumn, there will be so tides. So, here let us consider so the tidal effect on the groundwater level, and on the left hand side in the figure we are considering a confined aquifer. So, here this is the groundwater level. So, here although the ground slope will not be as steep like this generally. So, for simplicity, so the interface between land and ocean is represented by this vertical line, and so this represents a confined aquifer, and here so this tidal range is represented at 2h0, where h0 is the height of the water surface above the mean sea level at that particular tidal location or coastal location, and then at a general distance x measured from the coast. So, this is the coast here, which has been approximated as a vertical line. So, at a general distance x, the tidal height is equal to 2h. So, here what happens is, because of the tidal effect, so the when the water level in the sea is maximum, so obviously the groundwater level at that level will also reach that will also be reaching that maximum, and of course, as you move away from the coast, so this variation will also be decreasing, and eventually at some distance upstream from the coast, so this tidal variation will be practically negligible. And so, this is in case of a confined aquifer, and because of this, so there will also be this represents the variation of the piezometric surface in case of a confined aquifer. Now, on the left hand side, let us consider the tidal effect on the groundwater level in an unconfined aquifer. So, here, so there is an unconfined aquifer which essentially is spreading from the ground level here. So, this is the ground level all the way up to the impervious strata. So, this is the impervious layer, and similarly this is the impervious layer, in case of a confined aquifer, and of course, so this is also the impervious layer, the top confining layer, which is also an impervious layer. And in this case, what happens is the same phenomena is observed, and when the tide reaches its maximum range, that is its maximum level, so the groundwater level will also be fluctuating, and it will show the maximum level, which is h0 times above the mean sea level, and here in this case this represents the mean sea level, and at any distance x upstream of the coast. So, this groundwater table will be having an increase in the depth in elevation given by h, which is less than h0, and at some distance upstream of the groundwater level, so it will be 0, the groundwater fluctuation is 0. So, this is the impact of the tidal water level on the groundwater level fluctuation. Now, let us come to the effect of urbanization on the groundwater level. In this case, we all know that in case of urbanized localities, so there will be this large amount of households with say practically impervious surface or finished surface, and so which result in a significant increase in the surface runoff, at the same time significant decrease in the total groundwater recharge, unless and until so there are some specific artificial groundwater recharge structures are designed and installed, So, the groundwater recharge will be highly insufficient. So, therefore, this reduced groundwater recharge will result in gradual lowering of the groundwater level, unless until we take measures to have appropriate artificial groundwater recharge measures. So, therefore, the effect of urbanization in general in the areas is very what I should say is the reduced groundwater discharge possibly. So, here this is leading to unsustained groundwater levels. That means, eventually the groundwater level will be so deep that extraction of groundwater will become unfeasible and will not be feasible anymore. Now, so this is the effect of the urbanization. Now, let us also consider the effect of earthquake. That is EQ on groundwater levels. So, here what happens is, in case of earthquakes, there will be a variety of effects. As I was mentioning in my previous class, the earth shakes, and due to this shaking of earth, and there will be this various in the fault zones as well as in the various ones. So, there will be significant amount of damage to the earth, and especially in case of structures such as buildings and other engineering structures. And so, because of this cracks which develop on the in the buildings, which also continue along the ground. So, here what happens is, so there will be sudden rise or fall of water level in the wells. So, if there is a sudden rise in the water level in a well, so may lead to sudden rise or fall in well water levels. If there is a sudden rise in the well water level immediately after earthquake, then we should realize that there is possibly some additional very high groundwater recharge taking place due to the changes in the subsurface soil layers due to earthquake. And similarly, if there is a sudden fall in the well water level, then it is an indication that, so the water from that particular well is flowing into, say, neighboring locations, neighboring areas. So, thereby there is a sudden fall in the water level of the well. So, these are some of the impacts of this one. And now let us also consider, say, the impact of the land subsidence as well as external loads. So, these external loads as well as the impact of land subsidence on groundwater levels. So, in this case, both these land subsidence as well as these external loads, they result in a significant variation in the groundwater levels. So, here what happens is, wherever there is an external load applied, so this load may be due to a particular hydraulic structure, such as it may be a hydrostatic load or it may be some other load. So, here what happens is, due to the application of load, the ground shows certain amount of deflection, the soil above the aquifer shows certain amount of deflection, and when this load is removed, so this deflection does not really get removed, for the simple reason that soil is not perfectly elastic, and so there is a lot of plasticity involved in the soil, and because of this, so there will be fluctuations, there will be impact on the groundwater level. So, and then similarly this land subsidence, and many places this wherever there is a external this one external, wherever there is a say oversaturation of groundwater, so there the land becomes the soil, its unit weight will decrease from gamma sat to gamma sub. So, in this case in case of oversaturated soils, so this is gamma sat changes to gamma sat minus gamma sub, gamma W, which is the unit weight of water, and this gamma sat minus gamma W is the submerged unit weight of water. So, therefore, when the just below when the unit weight of soil is at or slightly below the gamma sat, so it will have the optimum moisture content and it will have the optimum strength, and as its unit weight falls, so its strength also falls. So, this strength, the fall in the strength is many times so significant, so that there will be land subsidence, and so this land subsidence, so maybe this landslide is an example of that, and so because of that, so this what happens is the groundwater level fluctuates. So, these are some of the impact of the earthquake, external loads as well as land subsidence, and so this one will now in this so this is how, so the groundwater level fluctuates practically due to various causes, various reasons, and so this fluctuation will result in the groundwater level which is either too shallow or too deep, so that wherein the extraction of groundwater level or harnessing of groundwater level becomes unsustainable, becomes costly. So, therefore, we should see that. So, by adopting appropriate measures, we should, by analyzing the groundwater fluctuation, we should ensure that the water table in case of the unconfined aquifer or the piezometric surface in case of the confined aquifer, it is maintained at the optimum depth. And so, in the so we will stop here, and we will continue, although I mentioned in the title of this one the literature, data sources as well as internet sources in this lecture. So, we will continue it in the next class. Thank you.